Very glad to be back in Athens. I've always enjoyed being here. Feel like I have so many good friends and made many friends over the years. I think this hotel was actually where I did one of my first stops a long time, 15 years ago or so. So it is definitely good to be back. This is one of the better views I get. Normally I'm inside a hotel somewhere to eat. So I will talk about energy modeling kind of throughout, but this is really a focus more on digital twins and how they can influence what you're doing. In many respects, they're just another model. And so that's one thing to keep in mind. It is just a digital model with a fancy term in another way. I'd like to start my talks by talking about energy. Energy and carbon are interlinked in many ways, but globally, buildings are responsible for about 30% of energy use. And it varies quite a bit. Greece, it's kind of close to 40% higher. Europe tends to have a little bit higher for that. But the two countries that kind of show the extremes are the third and fourth bars. That's China and Hong Kong. And China buildings are about 20%. In Hong Kong, it's 65%. So Hong Kong has very little industry and a lot of transportation, more than a lot of the countries you're seeing here. But that kind of shows the two extremes. China, on the other hand, at 60, 70% for industry. And so it depends, but globally, buildings are responsible for about 38, 39% of carbon as well, because most of our energy generation is based on carbon, whether it's coal or natural gas or oil or other things. It's important to keep in mind and keep in context. So, to give you context, I'll give you an example of the U.S. buildings, about 40% of energy use, look more for our residences than the commercial sector. It looked like 15 years ago that the commercial sector was going to overcome residential, with a bad recession beginning of the previous decade and downturns around COVID. Keep trying. So, for our residential buildings, yes, we have a mix. Heating a little more dominant in the U.S. because we do have water heating, cooling, refrigeration, appliances. But one of the interesting things is computers are already showing up in our homes, and the part that's more important to see is that the other uses, the small devices, the things that we carry around with us and charge. I have 25-year-old twins, and our son is living with us these days, and I wonder why my Wi-Fi is slow. I go on the router, there are 17 or 18 devices connected to the router. And so that's one of the things that's driving energy use today. That wasn't there 20 years ago. Commercials, this is across everything, so this isn't very easy to buildings are going to be very different. If it was a supermarket, a grocery store, that refrigeration would be 50%. But if we're looking at offices, cooling, lighting, ventilation, office equipment. But I think it's interesting, the office equipment and computing are now up over 13% total in the US. That does include data centers. Data centers are growing exponentially in the US. Where I live in Washington, D.C., just outside in Virginia, is a huge data center area. And part of it is that when the initial fiber optic lines were being brought into the U.S., they were all coming into Northern Virginia. And so 70% of the world's internet traffic goes through Virginia every day. But again, you see other uses are an important part. So if we're going to do anything about efficiency, we have to cover all of that. Our cities are undergoing massive change, urbanization. It looks like by 2050, we're going to see about 70% of the world's population are going to be based in cities. And that's a big change from just the 1950s when it was kind of the opposite, that it was only 30%. The other thing is that digitalization is helping the cities move forward, but there are a lot of other things going on. The aging and retirement is affecting a lot of countries as they don't have replacements. That's a concern even in the US that we are still growing, but primarily because of immigration, not so much births, but energy and environment, climate change, economics, finance, all driving what's happening. So here we get to be dynamic. Paris, this is a model of Paris that was created by a small plane flying back and forth over the city, collecting tens of thousands of pictures, and then that being converted through a process called photogrammetry. And you see, if you don't have good photos, you're going to have issues related to that. But if you have a high quality, you can get down to 10 centimeters, maybe a bit lower in resolution, and being able to work with that. But it's not just the plane. It could be a drone. It could be a truck running through the city like Google does in the US. It could be handheld, any of a number of things. And it doesn't have to be photos. It could be point clouds or the reality mesh or 360-degree images or obliques. So here's an example of a photogrammetry product that you can actually take pictures. The idea behind photogrammetry is you at least have a 40% overlap of what's going on. And then this is sent up to the server where then the model can be produced. It can be done on the desktop as well, but much faster doing it on the cloud. Yeah. So here's an example of modeling a city's environmental impact. This is from about 15 years ago. I think this may be Pope Francis's trip to the US. This is Philadelphia, halfway between New York and Washington. And what they did, they flew a helicopter, captured the city. Their concern was for security and making sure that they had all the parts there. So this 3D model then was brought into the BEMP product where they could bring in fencing and signage and being able to look at that. So pretty pictures, not terribly useful beyond just that. But that's what I would call a reality model. About 30 cities in the US have been doing building benchmarking. By law, the city owners, or the building owners in the cities are required to submit their utility bills for any building over about 2,500 square meters. And so they put this in a public database, and Philadelphia happens to be one. So I talked to one of my colleagues, I said, is there anything we could do to try to animate that to make it more digital? And so they have energy use data, fuel types, water as well for that. But the data from the city look like this. It's kind of hard to find things. But they have all the data available. But they're mapping, it's just that sort of simple mapping around the city. The city center is down there, kind of bottom center. So what my colleague did was then take the data that's in the database and then apply just a range of colors, red for high and blue for low, just to show just different aspects of that. So you can see some of the bigger buildings there. But again, this is just color coding. It doesn't really help. So the database itself has more information in it, and then all that information that the city has is now part of that model. And so we can look at an individual building. He's going to select one soon. And then all the data about that building is there available for it. The other thing that can be done, because all the data is there, I can start with the data and look at an individual location. I can look at the size of a building, I can look at a building type. In this case, he selected selecting a very energy intensive building, which is not surprising that it's a hospital. But so all the data is there, and that's the idea, beginning to get toward digital twin. This is not quite there, but the data idea is there. So digital twin. So it's a model. It's a digital representation of some entity. It doesn't have to be a building or a city or something like that. The idea of digital twins actually started out with NASA in the 1980s, where they were creating 3D models, and they wanted to simulate how things were operating within their space stations or the capsules. So they were kind of one of the leaders in this. But I think one of the key points is continuously updated from data from multiple sources about how that building is being used. It may not be instantaneous data, it may be every day or so. But the idea is to be able to visualize the asset, the digital twin, see what's going on, and perform analytics. That's really the key use of the digital twins today. So physical asset data being shared with its digital twin, where you can do the analysis and make decisions about that, and then decide how to affect the physical asset. And some of the examples of the data: schedule, engineering, enterprise data, geotechnical, geospatial, sensor, reality data, and any other data associated with it. So there's a lot of different ways you can deal with that. Different digital twins will focus on one thing or another. Some of the workflows can be not just 3D, can be 4D, 5D, construction modeling, logistics there, operator training. Colleagues have been working on using some of the VR modules to be able to interact in a machine room with the controls, and being able to access the manuals in the VR mode. Remote inspection is another important one. I'll show you an example of that in a moment. Can be very difficult if something is very high or dangerous. Maintenance planning, shutdowns, site survey, reality capture, and then also being able to use that as a way to work with any stakeholders. But it can be a full life cycle from concept and planning, design, engineering, construction, and into operation and maintenance. So let's look at an example of a digital twin. This is Cambridge University, and this is what they call their West Campus. This is not the historic core. It's a new campus out west of the city. This is actually a little bit old. The resolution is not very good. I think it's at least a decade old. This is a newer building called the Institute for Manufacturing, and they've created a digital twin of that particular building. They're showing some of the assets, particularly the plants, chillers, pumps, etc., that are in that particular building, and being able to look at that. So this is another view, but now instead of just sitting outside, we can go in. Outside's been done with photogrammetry, so that the drone's been there, but we can go inside with LiDAR or other things and begin to look at the machine room. And the quality is good enough that if you focus on some of the signage, you can read what's going on for that. But also the particular elements in the machine room are active. So I can go to a particular pump and I can pull up the information on that pump, its flow rates, see what's going on. So we have information, all the design information there, but I can also look at flow over the particular period and see how it's operating. So that's the idea of a digital twin, is we have that data that doesn't, you don't have to be there exactly. You can view it at your desktop or your tablet. Here's another example. This is Singapore. This is a new tower, so this is actually a BEMP model rather than a reality model. And these floors, these 6 floors, 9 through 14, are Microsoft's headquarters in Southeast Asia. And what they've done is tie in the building monitoring system data so that you can see the temperatures throughout the day in a particular space. They can actually look at occupancy and some other elements of that. It doesn't have to be just individual spaces. They also, you can look across the whole floor or the whole property as well. This is also in Singapore. This is Savannah Jurong's new headquarters building. They have created a digital twin starting from construction on through design and assembly. They've also looked at, in this case, they're showing how the solar panels are operating, what their temperatures are, what the voltages are being put out over time. Building systems, you can go to a particular floor, look at occupancy, you can look at temperature, but they also have green roofs, and being able to look at that element, and you can tour that as well. I was just in Singapore last month, and unfortunately didn't have time to tour that, but it's supposed to be a really nice space. Now, given the news of the past week with the funeral just this weekend, I thought I would add something about the digital twin that one of our partners created for St. Peter's. And they've did a combination of point clouds and photogrammetry. The interesting thing was they could not use inside of the silica because of the fragility of the artwork and everything else. They couldn't use a drone. So you see in the kind of middle left, they were using balloons to float the cameras through the space. They did use some drones, particularly outside. They did a lot of investigation using radar, georadar, and other things. They were trying to investigate the structural integrity, but also kind of document everything else related to that. They now have a common data environment, bringing all of that together. They're able to look at the data in real time so that they can see if structurally something's changed and be able to look at that and look at all the other information related to that. But so they wind up with a digital twin, which allowed them to also create a BEMP model from this, since they had the data related, and maintain that structural integrity, which was a big concern in a building that's over 500 years old. They also took the opportunity to scan all the artwork and the assets that are in there, allow them to set up planning for various parts, maintenance, how they're going to go about that, but also education and gamification, as they call it, create and simulate and play. So this is the promotional video that they put together related to that. A lot of this, of course, is just video of the like the Sistine Chapel, etc. And just about now, now we're at the digital twin. So we have the point cloud, we have the BEMP model, being able to look at the detail, the structural analysis, and also being able to look at all the pieces of it and being able to drill down, which was a really a powerful tool for them. But this was the first time they've been able to get that sort of resolution. You see the balloon floating. So this model, they said it's 20,000 square meters. And so it's quite a big model, but they're also looking at everything else going on there. So that's the idea, have the power. And you see this one is focusing primarily more on structural, but to getting other information. So digital twins are not just for buildings and just cities. Transportation, water, energy systems, cities in general, and mining all can have digital twins as well. Subsurface digital twins are beginning to appear, but of course not as much of that is there's not a lot of change going on with that. So if we look at transportation, here's an example. There's a digital twin of a city. There's the roadway. They're considering adding a new off-ramp for that. They can see what it looks like in context and see how it interacts with buildings and other things. Then with the modeling capabilities, being able to see how traffic would be on that highway. Here's another example. This is this could be Singapore. I keep forgetting where that particular one is, but they've done the digital twin already, and they now can look at individual bridges and be able to look at inspections. So there's one, the documents, they have cracking defects. They show all sorts of images related to that, and based on that, they can get a load assessment and see what the engineers would want to look at. So these are examples of some of the images showing some of the cracks and trying to determine whether they're superficial surface or truly a challenge for that particular one. Here's another example, but this is using VR. But this is what you can see inside the VR goggles. And this is to try to make it easier to inspect bridges. Bridge inspection is notoriously dangerous because you have to hang somebody off a bridge in a harness in a rope. And so be able to do that with a drone and capture this and being able to pull the information together and look at it at leisure in a safe environment is very important. So in this, they allow you to zoom in to various parts. And so you can see the condition of some of the underlayment, some rotting going on there. Steel looks okay, fortunately. But you're able to look at all the aspects of that without having to hang off the bridge. Another example, this is a roadway that they're about to do a repaving. And so they have a digital twin of the existing piece that's exported to the digital twin platform or the design platform. And let it catch up. And then the engineer can go in and look and see whether there are inconsistencies in the roadway, the existing roadway, and he can make adjustments to that to smooth out bumps. That information that gets fed to the cut and fill machines directly, so that they know at this place we need to cut deeper or we need to fill more. So definitely a positive. Water, stormwater, an important part of our infrastructure as well. This was using a handheld LiDAR device, the top left. This is the sewers of Paris, and they have absolutely no idea what's in any parts, but this was one way for them to be able to capture some of that. Here's another example. They've opened a hole in the street, and you can capture what's there pretty quickly. This only took like 10 minutes to be able to capture a model of that. But others using augmented reality at street level so that you can see where the utilities are below grade. And then another one here, this is the New Elizabeth line in London and showing how it interconnects with the city being able. This was a real challenge. They were within half a meter of some other tube tunnels that they had to be very careful with. This is a colleague in Quebec, Canada, and so she's has her VR goggles on, augmented reality, and she's able to see where the individual utilities, so the blue is the water line. She, rather than having to dig up the street to find things, she can indicate where they are, and you can expedite if you're trying to work on something. Another example, because of the accuracy of these digital twins, you can begin to look at issues of flooding. So the stormwater system here, this is Lisbon, is over 100 years old, and so it wasn't prepared for all the water that's coming in. So they can begin to look at where they're going to have problems and be able to improve that. One of my favorite ones, this is the Weather Channel in the US. They 24/7, they are doing weather. And this was before one of the hurricanes was hitting. And what she's doing is showing simulations, essentially a digital twin of what's going to happen with flooding, starting at 1 meter and then up to 2 meters. You know, cars are floating around and it gets very dangerous, but that's exactly the idea. And so that's not quite as dramatic as that, but here's Paris again, and looking at flooding of the Seine. You see that it's flooded the banks, and because of the accuracy, you know what is there. As the water comes down, which it will in a second, you can begin to see where just a small change in the embankment height would prevent flooding in a particular area. So that's another tool to be able to look at resilience for a particular case, particularly with places prone to flooding. I've only given you a couple examples, but cell tower inspection, another way that's we've seen digital twins used, electric power transmission, distribution, industrial or power plants, and even roadways. So you have the long, thin digital twin being able to do that. Also being able to do a railroad inspection kind of on the fly, literally capturing it as it's driving through and being able to see where issues might be. Other tools useful in this, agent-based simulation. This is simulating how people interact within a building. And here we have a subway station and being able to see how people get in and out very quickly. Working within a BEMP model, here's a design for a new subway station. They just have put 2 turnstiles in, and you see they have a problem. The 2 turnstiles is not enough to handle demand. So they're still within the BEMP product, they haven't left. And they're able to add in new turnstiles, and in the BEMP model, go back and re-simulate. So now they've solved the problem, and even in busy times, they're able to do that. So that's an important tool for being able to do that. Primary use of these is getting people out of large stadiums. I think this is Real Madrid. It was a relatively recent project related to that. So showing how people can get out quickly and safely for that. Other things we're seeing, this is not tracking individual cell signals, but it's tracking the fact that there is a cell signal and being able to see where traffic is based on time of day down there in the bottom left. And you see how it fades over the US with time. Here's another one. This is Singapore beginning to look at a new development going in, and they want to look at not so much that animation, but look at what happens if they add new traffic in the area and see where they're going to have problems. So that's an important part of having that traffic model, because Singapore already has massive issues with that. So taking a look at urban digital twins, we're now trying to get away from just individual buildings and important ones. This is the headquarters for a large electrical manufacturing company in Germany. They've been on this site for 120 years, but they have a twin of the whole site, being able to look at floor area for various things. They can look at, here's noise map related to that. They also were planning to put 2 new buildings in. They can put them in from the BEMP directly into the digital twin, take a look at all of that, see how it interacts with all the utilities and the site. You can turn on the various layers and show what's going on. You can also look at just one individual pump or even a pipe for see flow rates. Change the transparency, be able to look at how that's in context. And in this case, they actually had an inspection at a particular pipe. So you can go in and see that, all part of the digital twin. Another city scale, this is Helsinki. This is their 2nd generation model. Resolution is about 10 centimeters. You see some issues with some elements of it. It's a pretty nice model, but they recently did another one, but this is using that 1st generation. They were worried about flooding. The city's pretty much just barely above sea level. So they were trying to see where water would, that top middle left is the main harbor. But their main cathedral square, the cathedral's fine, but most of the historic part of the city would be flooded. And so one thing they were looking into to improve. But this is the 3rd generation, 26 square kilometers of the city. And they also use machine learning, deep learning, to start to automatically extract what things were. So no longer is it just really a 3D picture of what's going on. Being able to look at what's a roof, what's vegetation, what's transportation, etc. So they've been very advanced in how they're working with that city. This is from the Helsinki city website, trying to look at the cases of these models where we could use carbon neutral, smart, web services, education, city marketing, tourism, all sorts of activities where they can be used. The green dots mean they're doing something with it. The red means they have not. Blue, they're beginning to consider it. So it's they see a real powerful use of the digital twins for that. This is the largest digital twin I'm aware of. This is Ahmedabad in Gujarat, India. This is just a 1 by 2 kilometer segment of that. The whole model is 450 square kilometers. And what they've done is, it took them about 18 months. They flew a drone over the entire city, collected all the information to start at least with the reality model. And what that looks like is you have the mesh surface, but you also have the no color, and then you can see the mesh underlying. And the idea was to use machine learning while they're creating the model to begin to look at some of the data related to that. So that's what the point cloud output looks like. It's beginning to understand what things are, but as you see, there are a lot of fairly low-rise buildings. 2 to 4 stories is pretty typical, and a lot of trees. So this is using machine learning to be able to start looking at, can we draw back the trees and see where the footprint is. And the footprint becomes important because what they were able to do from that, knowing the building height, what businesses or how many families were living in a particular building, they were able to create energy models of every building in the city. And some of the machine learning helped on the larger buildings to be able to identify windows and help in creating those energy models as well. It's an automated process rather than doing individuals. They do have energy bills and water information for each and every building as best they can. There's some places where it's difficult to tell where wires are going. But here's kind of a look, the central part of the city. there, the reddest part. Most of the cities you see is residential, more on the low-rise side. There's residential again, and then looking at that plot that we were looking at beginning, so it's a mix of residential, commercial for that particular case. This is looking at energy use intensity. You can see the red buildings are well, in this case, I'm sorry, that's just commercial. But if we start looking, there's water consumption. You can see the towers use more water, not surprisingly. Not normalized area. Energy use intensity, again, the bigger buildings, the commercial buildings primarily are higher energy intensity. Again, like the model I showed you of Philadelphia earlier, it is possible to look at individual buildings because they were able to simulate it probably within 15 to 20% accuracy, because there's a lot you don't know about each building. But they're able then to look at the in-use breakouts and begin to look at what would be possible. Similarly, water and pumping energy related to that, not surprisingly high for this particular building. And what they did was create a whole model of the city and being able to look at particular elements of that and start off with a baseline where we are today based on simulation and the utility bills and the other data, this focusing on cooling. And then on top, they were looking at what is the opportunity for retrofitting the buildings, which are the best candidates for that. And because they have the energy models, they can run through that. The ECBC is their national energy code, and that was seen as kind of a baseline for being able to do that. So, and from this, they're able to decide where to spend money first, which are the worst buildings and which can be done. So you've already seen a little bit of the Singapore, but here's the model of Singapore itself. So they have areas that are focusing on greening, looking at solar potential throughout the city. They also do building performance. I think these are not normalized to square meters because it's all around the big buildings, but also they can look at water use, various systems there. Also traffic, which is a problem in Singapore. They only have a few main highways to be able to get through, and they can see that from various parts. So that they're using this as a planning tool, but also looking at scenarios. So that this is the first national scale digital twin I'm aware of. I know there are activities all throughout Europe working on this right now. So why do we need to bother? Well, if you look at the UN SDGs, cities have issues that support sustainable development goals. So urban and real estate development, asset and infrastructure management, environmental intelligence, climate monitoring. You can see all sorts of activities there. Transportation, mobility, optimization, energy production and distribution, and public safety and security. One of the things that I will say I've seen digital twins, a lot of the work early has been to look at transportation and public safety, being able to have that information so that they can get emergency vehicles out quickly to where they're needed and being able to have information like that. So that's a powerful tool. So cities are right for using that. They may not use everything. I've seen transportation and public safety being the first two. The other things digital twins allow us to do is that simulation and monitoring, which you saw for on the bottom. That visualization. Many people don't read plans very well, or maps, or even understanding. So if you can bring them into the system and make it immersive, be able to see what's going on, that's important. The analytics can be visible, insights through AI and machine learning, lots of opportunity there to see things with something that's complex, AI tools can help you find things that are not there. Decision support, and I think that's one of the key things is as long as the data are getting actively redone, you can add that. The other thing I haven't mentioned is digital twins not only being updated for data, but because they are, it's just a platform. BEM models can be brought in, buildings can be changed out. It's not a hard thing to keep that up to date. A lot of people say they achieve many hours of cost savings, time savings by using digital twins. The consultant that was doing St. Peter's said that they saved weeks of time because they were able to capture information that would have been very difficult to do otherwise. It would have to set up scaffolds and all sorts of things otherwise, which would have interfered with normal operations. But sustainability, of course, being a key thing. So digital twins, very powerful to be able to use in many different areas. Urban planning, sustainability, mobility, planning coordination, energy, construction workflows, so looking at 4D and 5D activities there, public space improvements. A lot of the mapping tools actually evolved out of the ability for places to involve crowdsourcing of information. So they're putting a new park in, what would the inhabitants of the city want to see? And that's kind of important. Emergency response, urban accessibility. Another small town used it to do an inventory of where they had appropriate curb cuts for wheelchair access around the city, because it was going to take them longer to go each place. They were able to fly a drone and be able to do that very quickly. So in summary, digital twins make it easier to understand not only our buildings, our other infrastructure, how they fit in the community, and how they interact with the environment. It's a federation of data. It's no single platform that needs to be done. There are lots of different ones out there. The reality models can be from photos or point cloud or mesh, however you wanted to deal with that. Data becomes really important, otherwise it's not really a digital twin. But the analytics and the detailed BEM models are there. So not a single vendor, data provider, or platform. There are multiples out there. And the best part is that federation. Being able to bring everything together in a platform from different data, from different sources, and different models. It does provide a holistic way of looking at individual buildings and evaluate risk, resilience, and sustainability at that individual level, but also the community and city scale across many different disciplines. So look at how the buildings interact with everything. With 5G making its way into use, what I'm seeing is a lot of connections. The buildings, smart buildings, the IoT portion allow us to get to smart cities, so that 5G is enabling that in a very fast way. Fast in terms of latency, speed response, not so much just because we have the data speed. And digital twins enable 3D to 7D. And if you don't know, 3D geometry, 4D is time, 5D is money, sustainability is 6, and facility management 7. So you can pull all of that together in one way. And another way of looking at it, a reality model with actionable data becomes a digital twin. But if you have a digital twin and AI, I'm seeing the term digital triplet come around. But as you've seen, most of the activities that we've done already incorporate that the idea of using machine learning and AI in specifically. So that's I'm not sure that we need a new term to describe that, because I think that's already there. Anything related to data can be dealt with by AI. So a couple last things. not related to my day job or ASHRAE. I have had a career-long interest in climate data because as an energy modeler, that was one of the things that was very difficult to find. So we now have, this is a partner of mine, she and I put this together over the last decade, and last year we published a new data set with data through 2023 with about 17,000 locations globally. So if you look at Europe, there's pretty good coverage. And so that's a free resource if you're using energy modeling at all or need climate data, that is available. So with that, I'll be happy to take some questions.